Good morning, everyone. My name is Viroon Kamchoom from KMITL. So today I would like to present my research that we have been doing in KMITL. So my title for today is Nature-Based Solution for Enhancing Infrastructure Resilience under the Climate Variability. So first of all, I would like to say apologize for everyone here because I am on traveling the way back to Bangkok. So it might not be convenient for me to present this. So I need to record this Zoom video. And if you have any sessions, so you can drop me the question during the Q&A. I will be access to the Zoom and also answer this question. So first of all, I would like to introduce myself. My name is Viroon Kamchoom. I'm an associate professor in civil engineering at KMITL. I'm also the head of research center for green and sustainable infrastructure, and also have been the editorial board member, and also be the part of the committee member, both in local in Thailand and also overseas for the ISSMGE for TC 104 and TC 106. My research is mostly related to how we can improve our infrastructure to be more sustainable way. This research has been granted by the local funding and the overseas fundings, and we also have a number of active collaborations. So I would like also to welcome you all if you are interested, and we have the similar research. So we can start our collaboration as well. And before I'm going through all the research, I would like to make a short introduction about our university. So the full name of our university is King Mongkut Institute of Technology Ladkrabang, or in short, KMITL. So we was ranked first in Thailand for research and industry income from the Asian University 2022 by Time Higher Education. And we again ranked first in Thailand for civil engineering and structural engineering from Saimago in 2022. Our beautiful campus is located in Bangkok. So it's just right next to the Suvarnabhumi airport. So if you guys have any chance to drop by Bangkok to the Suvarnabhumi airport, so you can just let me know so we can have a trip, short visit to our university and to see our facility as well. So today presentation, I would like to emphasize on the need of green infrastructure. What we are concerning nowadays, as you know that we have a lot of problem from our construction industry. So we have a lot of CO2 emission from the construction, quite significant. We have we contributed around 30% of the total carbon emission in 2019. We was ranked as the third position after the energy and transportation sectors. So of this, it seemed to be okay. However, if we look back 20 years before, we have been rising our carbon emission in the construction about 74%. This is quite significant, and it will become much more worried if our government invested in a lot more infrastructure in the future. So again, if we look back, our design and the development in construction, so we can see that there is the reduction of the cost and the carbon together. So we have been improving our design, and with that effective design, so we can reduce the cost and the carbon together because we minimize the use of concrete material or steel that is very conventional material, which are high carbon embodied material. So within this case, we can drop the carbon emission significantly. However, we are now at the tipping point in construction. So if we want to lower down the carbon emission further, so we need to find the substitution material, which may be highly cost and it's not feasible in terms of economics for construction. So the duty of we are academics and researchers, so we have responsibility to improve that, to find out whether that we have the low cost and low carbon emission material in the same time, so that it's become feasible for our construction industry. So I think one of the solution is we can look at the nature-based solution. If we can see in the figure here, we can see the plants play the major role in the carbon storage, because when the plant provide transpiration, so they can store the carbon as the cellulose within itself. So this provides the largest pool of the carbon storage compared to the living material. So when we consider the nature-based, when we consider tree to integrate it in our slope or infrastructure, so we can provide the largest carbon storage. And also, again, planting tree also provide a low-cost solution, improving our environment as well. So we have the great potential because our Southeast Asia is one of the largest top 3 global biodiversity. So we can make use of these resources to improve our facility. So by using the nature-based solution, we may consider planting the grass and the tree on the slope. So as you can see in the figure, the root of the tree can penetrate down to the slope, and this can provide an increase in the shear strength and hence provide a mechanical root reinforcement to the slope. And again, the tree, the grass also, they are living material, they need the water. So when they remove the water out from the soil, so the shear strength also increase. And hence this is the dual contribution for mechanical and hydrological improvement to the slope stability. However, we need to be concerned because these living material can be growth and decay as well. They might have the benefit to restore the function, to repair the damage of the root. They can produce a new root to provide reinforcement. However, we need to understand that variation as well. So come to the point that we need to consider. Nowadays, we have a lot of problems from the climate, so that we have the extreme climate, a lot of rainfall, intense rainfall that might have the slope failure. And again, our embankment that might made from the clay, fine grain material that they can shrink and swell a lot during the seasonal variation. So this can happen and provide a problem to our serviceability. So, and this can be accumulated year by year, and at the end of the day, they can generate the progressive failure. So once we integrated the plant in, so the plant also play the significant effects to this stabilization. So the plant can provide reinforcement and soil hydrology, but then we need to see how that effect can be. And then we also have the effect of the growth and the composition of the root that can change in the property of the root and change in the pore space of the soil, which eventually affect the slope safety and serviceability. So we need to consider that is the soil bioengineering method here is capable of improving both safety and serviceability of infrastructure or not. So in this research, we will dig down into this. So I would like to start with the small scale first. We are studying in the lab. So we plant the glass in the column, and then we divide it into 2 parts. So the first part, we use it for the direct shear test, and the bottom part, so we use it for the tensile test. So the direct shear test, as you can see in the figure here, we put the soil in and then do the shearing. So in this case, we can see how much the shear strength can be improved with the existence of the root. And also we do the tensile test to pull out the root so that we can see how much the tension of the root can be resist. So we are not focusing on only one particular age of the plant. We are studying during the growth period, whether 1 month, 2 months, 6 months, and we also kill the plant by different approach, either burning and herbicide, and wait for a long time so that we can see the gradually decay of the root material. So we can have the complete property changing of the root along the edge as well. So in this case, as expected, we can see that tensile strength of the root is improving along the growth period, as you can see in the top left figures. And then once we kill the plant, we kill the plant by herbicide. So the chemical put into the plant and the root was killed immediately. So in this case, the tensile strength of the root was dropped very significant and very fast. So compared to another approach, we burn the plant. So when we burn the plant, the root inside the soil was naturally decayed, and that decay process is much slower. So we can see that the plant can still maintain the tensile strength until a longer term, let's say 360 days. So the tensile strength can be reduced substantially. And again, with the nature-based solution, we try to bring in the other living organism. We bring in the fungi to improve this tensile strength. We can see that during the growth period, the tensile strength have been improved with the integration of the fungi, and also it remains much more once we integrate the fungi into the root, even during the decay. So this can provide the suggestion to the engineers that we can also use the root and need to be concerned during the decay, and then we can also integrate the fungi into that to improve this reinforcement. And not only the tensile strength of the root, once the root is penetrated down to the soil, they can provide reinforcement to the soil, increasing the shear strength. But this is subjective. It related to how much the root is in the soil, and also how the orientation of the root it is. So in this case, we have the solution by planting the root in the lysol box, which we can see the distribution, the magnitude of the root along the depth very clearly. So we plot out what is the root biomass or root area ratio, the diameter, the orientation of the root, and eventually we shear it in the shear box. So with the shearing box test, with the direct shear test, so we can see that on the black dotted line is the bare soil here. And then once we plant the tree, the vetiver grass in this research, so we have the significant improvement either from the red or the blue line. There are the different species of the vetiver, but both of them improve the shear strength significantly. So in these situations, we can also find out what is the cohesion friction angle that improve from the reinforcement of the root. And then we can suggest these parameters to the engineer for the design, then incorporate in the construction later. So, and as I said that we also indicate this into to study the different age of the plant as well. So we can see during the growth period at the early time here, so the shear strength was improved quite significantly. But then once we kill the plant, the decay started. With the herbicide, so we can see that the shear strength was decreased quite significant, and it's almost decreased even below than it was for the bare soil without any grass. For the decay process, once we kill the plant by burning, so we see the shear strength also drop down much more, even worse than it was for the bare soil. So we are not trying to oversell this knowledge that we try to use the nature-based solution in that. It might provide the positive effects, and also it might provide the negative effect. But once we study very complete here, so we can see that we can have like the solution, the suggestion to the policymakers if we found that the plant has been damaged. So if it was decayed by the herbicides, so within 2 months, so we need to find alternative or mitigation to suggest and improve the stability. So we have time span between 2 to 4 months. In this case, we can find or suggest the alternative mitigation. And again, we would like to go a little bit in the bigger pictures. So we would like to see the safety and serviceability of the slope. So for the safety of the slope, we will just make the slope model. So in this case, we employ the geotechnical centrifuge machine. So some of you might not know what is this machine can be used. So this machine, once we put the small model, a reduced scale model into arm, and then we spin up. So the model will receive an enhanced G level. So as you can see from this equation, so once we increase the G level, so we can reduce the size of the model, and then the model still have the same stress condition as in the bigger prototype in the field. So as you know, the soil is stress dependent. So the same soil in the shallow depth and the deeper depth may have different behavior because of the stress that they receive are different. So with this machine, they can allow us to use the small scale model with the enhanced G level, and then it can have the same stress and it can be comparable to the bigger model in the field. So in this case, we use the slope model, as you can see on the right figure here, and then we embedded with the plant model. We made the plant with the cellulose acetate, which have the similar mechanical properties with the real plant, and then we connected with the pipe with the vacuum source so that we can simulate the transpiration of the plant. So in this case, we can simulate both mechanical reinforcement and also transpiration as well. And once we already, once the slope has been was ready for the test, we spin it up and then we apply the rainfall in flight to fail the slope. The rainfall can be applied through the nozzle, and then we have the instrumentation to measure any infiltration of the water by the water pressure sensor. So I would like to highlight the key important thing here. As you can see, for the 45 degree of the slope, we doesn't see any failure of that. That means we have with the root inside that, with this configuration of the root, so it's sufficient to maintain the stability. So we want to go more extreme than that. We increase the slope to be 60 degree. So we can see either we put the tap root or the hard root shape with different geometry. So both of them still fail. So again, we don't want to oversell this one. So we can see that even though the tap root has been failed after 3 hours, but the hard root provide better stabilization, they can delay the failure to 5 hours, but then it still fail any case. So that means that the nature-based solution by using plant here is only good for any slope that less than 45 degree, and any steeper slope than that, we may need to rely on the conventional mitigation, let's say the retaining wall or retaining earth structure. However, this is already a good contribution because if you can say that 70 to 80% of the man-made slope that we have are not that steep. It's like 30 to 40 degree that is already steep enough. So if we consider that amount or number of the slope, if we can replace it with the nature-based solution, so it can improve and reduce a lot of the concrete that need to be used. So this can be another alternative and suggest to the engineer can be considered on this. And we also consider the serviceability as well. So in this case, we go into even bigger scale. We conducted the full-scale test. This research has been supported by the funding from NSFC in China and also the funding from Thailand. in this full-scale embankment, we divided the zone into 6 different zones. In the fourth zone, as you see from the figures, that is planted with the vetiver grass, and in the middle 2 zones, we left it bare for the comparison. And we have a number of monitoring sensors. So we have the weather station, so we can have the climate parameters, and we also collect the historical climate from different stations. And in combination of this, so we can calculate the climate index, which can tell us whether that the current climate nowadays that we have is already extreme compared to the historical climate or not. And with all this data, we can also predict the extreme climate that is going to be in the future as well. And not only the climate module, we also have the measurement for the plant module as well. So in this case, we would like to see the development of the cracks and the root inside the embankment. So we put the transparent acrylic into our embankment. So we put it there and we put a mini camera into the tube so that we can take a photo, 360-degree photo along the depth. So in this case, we developed the mini lysotron with this camera, as you can see, and then taking the photo and put into Python, and then we can do the image analysis from the photo. So with this procedure, we can get the root area and also the crack area that develop differently along the different seasons. And then we can also have the temperature measurement for the leaf and the soil so that we can calculate for both evaporation and evapotranspiration as well. And for the soil measurement, we have the suction measurement or the negative or water pressure measurement, and also we also have the water content sensors so that we can measure anything, the response of the soil along the season. And for slope displacement, we have topographic survey, and then we have the drone taking a photo, and then we do the 3D reconstructions so that we can have the profile that's changing along different seasons. And I would like to highlight the keyword, the key finding here. If you look at the figures on the top, this is the photo that we took it from the different zone, so from the bare soil and from the vegetated soil in the same time, side by side. So you can see from the bare zone, we can see the big crack that developed in this particular zone. However, all the cracks has been minimized significantly in the vegetated soil. We can see almost no crack in the area that we have the root penetrate down, and we have only minor crack far away in the area that we doesn't have root. So this is in agreement with the result along the depth as well. So we can see in the figure below, we have a lot of cracks, especially in the drying summer in the red color. And then once it got the rainfall, the crack has been minimized, and then it become more again in the next summer. But compared to the vegetated soil, the crack has been well maintained within 2 to 4%. So this is quite interesting because we can see that the root can maintain water content we observe from the water content sensor. And then with that the maintaining of water content, they provide the less fluctuation in the water content. Of course, they come with the less the crack that can develop as well. This is quite very important from the engineering perspective, because if you think about it, when we have the clay embankment, the rainfall coming in, sometimes we got the rainfall, the monsoon rainfall during the dry summer. Usually the clay embankment, they have the low permeability. The water cannot get in easily, but once we have cracks, so the water can get in and then can eliminate the stability very, very quickly. So with planting the grass and the tree here, so we can minimize those cracks quite significant. So it can be the major contribution to be considered as well. And we can see the contour of the formation here as well. We cut the section from the bare soil at the top figure and for the vegetated soil at the bottom figures. So we can see the original condition, the slope contour are pretty similar in the black dotted line here. Once the slope has been settled, we can see after 6 months, the slope has been deformed quite significantly, and similarly for both bare and vegetated soil. So this is because of self-weight consolidation. But the interesting thing is that after 6 months for the bare soil, there is a gradually deformation happen, but is also well maintained for the zone with the vegetation. So that means this is make me want to go deeper detail. So we cut the point from the top of the slope and the bottom of the slope, and we see that this is the result from the settlement from the top slope. The bare soil in the brown color keeps settled along the time. It's like consolidation settlement. But the plant, on the other hand, after 6 months, they become more mature, and then they can provide the reinforcement and maintain or reduce the settlement that you can see. The settlement has been minimized almost 50%, and already big contribution on that. And if you can see from the toe slope, in these figures, for the bare soil, it keep moving outward and outward. So this means that if we have the top slope settle down and the toe slope, it tend to move outward. So that means our bare slope without vegetation is not really stable. It tries to fail all the time. But with the plant in, we can see the fluctuation though, but it well maintained within the zero value, so that the plant also not only minimize the settlement, but also will maintain the shrinkage and swelling as well. So this comes to the good conclusion that we have been studying the shear strength over the growth and the decay period to study the root biomechanical change, and can suggest the parameters to the engineer for the design as well. And of course, we study about the plant that could stabilize at 45-degree slope, which a big contribution already, because most of the slope not that steep up to 45 degree. And then of course the root can also minimize the cracks, preserve the reduce the moisture fluctuation, and that can contribute to the stability as well. And of course, the plant, as you can see, that can minimize the settlement by up to 50%. So that is also another contribution that we can consider it. So in this case, we can see the plant can improve our safety and serviceability of the slope. So before, I would like to give final note about achieving the net zero. So in today that we concern nowadays, we are concerning a lot about the carbon emissions. And as you can see, that carbon emission nowadays is mostly from the earthwork and the pavement for our construction industry. So if I try to calculate the carbon emissions, so we can see that with the conventional material, we got the carbon emission up to more than 30,000 tons per year. But once we try to integrate the glass and the tree, so the glass and the tree actually can provide a negative carbon emission, or we call it carbon sequestration. In this case, in the total, in summation, we don't need 100% usage. We don't need to use the glass and the tree for every earthwork and pavement. If we use about 70 to 75%, we can already achieving the net zero, which is already important and contribute much more to our country already. So the final note that I would like to give to you, there is always the risks in the engineering. We need to maximize the social benefit while minimize the human risks. So what can be the risks though? If we use the nature-based solution, so of course there can be the risks of the variability of the plant species, of the growth period of the different geometry, and even the growth and the decay period. also provide the effect on our property and reinforcement and stability as well. However, all these factors, we are engineer, we are academic and researcher, we can study that, we can consider that as I presented in this presentation. On the other hand, there is also the risks if we are not using nature-based solution. Of course, if we rely on conventional material, so we need to use high carbon embodied material, and that provide the richest cycle, and they are worsen the climate, and we need to even use more material, more carbon emission. Up to the certain point, we are beyond the critical point that is not reversible anymore. So we need to balance out the risks of using it and not using it. So in my case, I think I would like you to consider to taking the risks if we try to use the nature-based solution for the further improvement of our future generation. So all of this work, I would like to thanks to the contributors, especially to my PhD student. Both of them come from Indonesia as well. So I'm really glad to be the advisor and also the contribution from all my colleagues, both from local and the overseas as well. So before I would like to end this presentation, I would like to provide a little advertisement. I'm opening for a PhD opportunity as well. So we have the funding for the income, monthly income, research material, and tuition fee as well. So I hope that you would like to consider that and try to enjoy the food and also the time in Bangkok. So I think I have a good track record because I also already have 2 Indonesian students. So I would like welcome all of you, the potential student candidates that would like to study further in our university. So last but not least, for those who are interested in going to the conference, we are going to organize the 18th Asian Regional Conference on Soil Mechanics and Geotechnical Engineering in Bangkok in 2027. So I would like to openly invite you, all of you, if you are interested, so you can join this event. So that's all for my presentation. And I would like to say terima kasih for all of you to join this event. And if you have any questions, so please let me know. So thank you so much for this presentation, for this listening.